This is the first lecture that's going to explore what's called wave-particle duality. Wave-particle duality is a central um, issue in what makes quantum mechanics or quantum physics interesting and different from classical physics. Yeah, so understanding wave-particle duality, or at least understanding how it is an issue or what's interesting about it, uh, is central to understanding why they're like how quantum mechanics addresses issues like wave-particle duality. Um, there's probably better ways to say that. And maybe in these lectures I'll be a little bit cleaner with the language because we'll have more in common in how we're using the language. Um, but yeah, so this is a central issue in quantum physics, and I'll put a semicolon. It's interesting and different from classical physics. In classical physics, there is no wave-particle duality. So in this first lecture, I'm going to start by addressing the wave-particle duality for the phenomenon of light. So light is, you might say, it's a set of phenomenon, I guess. Yeah, so a set of phenomenon. For example, we use light to see by with our eyeballs, and photosynthesis is based on light. Uh, Also, that's how our phones communicate with each other. There's a lot of light around, of course. It's how we know about the stars, for example. It's also how you know you have a signal that um, something is really hot if it's glowing, like glowing red hot, or white hot is even hotter. Okay, so yeah, so set of phenomenon, all sort of centered around this idea called light. And in particular, for the wave-particle duality idea, the question is how do we understand light? And in particular, so I'll put that is, how do we model light? And this word right here, I'll put it in italics, that's the big word, model. How do we model light? So the duality is that we actually end up needing two very different seeming models of light, and this is the duality. Right? Duality implies two, and we need two very different models of light to successfully think about light in many different circumstances or many different sort of settings of observing the phenomenon of light. And so this is the duality. The two models are known as the wave model and the particle, and I'll put, or photon model. So the idea of a photon is a very different idea than the idea of a wave of light, a light wave. All right, so the first thing we're going to do in this lecture, first lecture, is talk about the wave model. All right, so so I need to explore the wave model carefully and use it in certain circumstances so that we can explore certain phenomenon that are successfully described by the wave model. And we need to be really careful about what makes actually I'll put this above. So let's keep in mind this particular thought. So let me put it a line down. So let's keep in mind, what makes a model successful? Right, that's a question. Or, yeah, so I'll leave it like that. What does it mean for a model to be successful? And also, what does it mean for it not to be successful? So, in order to do this with light, to really understand this wave-particle duality, first we have to understand the two separate models themselves. And then once we understand the two separate models, we can try them out and check their success, is the idea. So the wave model for light. So this comes from what are called Maxwell's equations. So Maxwell's equations, let me put it in capital, are the laws that govern everything. This is the idea. Maxwell's equations are the laws that govern everything about electric and magnetic fields. Yeah, so Maxwell's equations are kind of like a summary. There ends up being 4 Maxwell equations. And these 4 Maxwell's equations, what they can do is, let me put this in bullets. So Maxwell's equations, what they do for us is they tell us how the electric and magnetic fields must look throughout space, right? This is a spatial dependence, right? And so sometimes spatial is, it's kind of like we're setting ourselves up to be able to give functions of x, y, and z in 3D space, right? So Maxwell's equations are about this spatial dependence, or yes. So these also, electric and magnetic fields, these are actually also vector fields. So Maxwell's equations also they tell us how to understand the directions of the fields everywhere in space. But what's more, and in particular pretty important for this discussion here, is also how the electric and magnetic fields vary in time as well, right? So we have this time dependence. So Maxwell's equations have a time dependence aspect to them, and Maxwell's equations also have a spatial dependence associated with them. And the wave model actually, right, the wave model comes from Maxwell's equations, right, comes from Maxwell's equations. So it turns out that you can do a little math with Maxwell's equations, and what pops out is a prediction, right? This is just from Maxwell's equations themselves, is a prediction for a traveling wave, right? It's not necessarily called light yet, but this traveling wave that can deliver energy, and also the truth is information, right? That's how, so you can encode information in this light wave. So, so Maxwell's equations predict that we can, or that nature includes a traveling, in particular, electromagnetic wave. It's a traveling wave in the electric and magnetic fields, and this traveling wave can deliver energy information, right? And so that travels at the speed of light. So the idea is since it is a electromagnetic wave and it travels at the speed of light, and you can deliver energy like warmth, say from the sun or a star, and you can make radio waves, right, to deliver radio wave type information around and listen to music with, or deliver music information. And if it travels at the speed of light, then it must be that Maxwell's equations have predicted light. So, but let me include, though, have predicted light as a wave. So Maxwell's equations give us a model for something that fits the bill to behave like light, and this model describes it as a traveling wave. It's got a wave equation that looks just like wave equations that Newton's laws of motion would predict, like for waves in materials. Yeah, so it looks a lot like a mechanical wave, but this absolutely is not a mechanical wave. The wave model for light is um, it's like, so this light wave is a traveling disturbance, just like sound waves and mechanical waves. Sound wave is a mechanical wave, an example of a mechanical wave, but this light wave is a traveling disturbance, not of a material medium, but it's a disturbance of the electric and magnetic fields in space. So you might say that the medium that carries the disturbance is the fields themselves. You know that you can have in space the value of field equals to 0, but that field equals to 0 can be disturbed, and this is the idea. Yeah. So, so this is where the wave model of light comes from. So there are some details about this wave model of light. Lots of things you can say. So let's continue with the wave model of light. And in particular, what we're going to be studying is best described as plane waves. Remember, a plane is a shape. Like we can talk about the plane of a piece of paper. So somehow these waves have a plane shape, a planar shape. So let me just make sure you keep this in mind. I want you to remember that everything that's going to unfold on these pages, it comes from Maxwell's equations. Maxwell's equations predict plane waves and light waves, but they also make really serious restrictions about the nature or the qualities of these waves. And I will bring up some qualities of the waves. Yeah, so as the discussion unfolds. Okay, so an electromagnetic wave is a pair of waves, and it is always a pair. That's one of the restrictions. It's a pair of waves, and here is an example pair. An example pair could be given by the following two traveling waves. So here is the electric part. It's equal to some vector called E sub 0, which is a constant, multiplying a traveling sine wave shape. And I just made a mistake. I didn't mean to put x here as the position dependence for my traveling wave. I'm going to put z. And in your mind, I'd like to remind you that the relationship between x, y, and z, for example, might be the following. So let's put, let's see. So let's do, yeah. So x is, say, the direction out of the page over here. Y is the direction out of the page, sort of this direction. X is this way. So we'll go X, Y. And what we have is referred to as a right-handed coordinate system if Z, right? So these are the I hat direction, this is the J hat direction, and this is the K hat direction. And the right-hand rule, remember, is that I hat cross J hat is positive K hat according to a right-hand rule. So I hat cross J hat is K hat, not K hat, right? So it's upwards, right-hand rule. So these are the relationships between directions, and I just gave you one piece of an electro and magnetic wave. So that's one piece of it. And the other piece is the magnetic component, and it is equal to a magnetic vector constant times the very same wave shape in all respects. Another restriction from Maxwell's equations is that for an electromagnetic wave, which is a pair of traveling waves, one for the electric part and one for the magnetic part, they always come together. That's a restriction. And they always have exactly the same wave shape, right? That is, they have the same dependence on space and time, precisely the same dependence. Okay. So there is some qualities that I can pick out really quickly. So it turns out that there is a wavelength quality to this electromagnetic wave, and the wavelength is common to both the electric part and the magnetic part. They have the same wavelength, and that wavelength is actually related to this thing called K. So it turns out that the wavelength, lambda, so this is the wavelength of this is the spatial wavelength of our wave, is 2 pi over K. So the point is, I think this is interesting to point out. So there is a spatial, location dependence. So dimensionally speaking, Z is a length. But you can't take the sign, right, the argument of the sine function. This is only allowed to be an angle. So everything inside the parentheses has to be an angle. And this angle actually is a function of position. So it's got this prefactor, this thing called K. It's referred to as the wave number. And this prefactor needs to multiply times a length and return an angle. I need an angle to sit here. I also need an angle to sit here, but that part of the angle depends on time. This part of the angle, right, the angle is the argument of the sine function here. This part of the angle needs to be space dependent, and so it turns out that the thing called K must be 1 over length. And that's, so I've got this, so if I have K on the bottom, I have a length, right, called the wavelength. This wavelength is referred to as the spatial periodicity for obvious reasons, or I hope it's obvious. There is also a thing called a period, and the period's often given the symbol capital T, and it's associated with the omega part right here, so 2 pi over omega. Typically, we talk about frequencies instead. So frequency is actually the upside down of the period. So it's, if the period is 2 pi over omega, the frequency must be the upside down of that, omega over 2 pi. And if you wanted to, you could talk about a spatial frequency, but nobody ever does. Everybody only talks about the wavelength itself. So it turns out that the speed of this traveling wave is referred to as the phase speed, and I'll tell you why it's called the phase speed. So the phase speed, or the phase velocity, is omega over k. So omega is like an angle per time, and k is like so anyways, it's dimensionally, you can see that this is going to turn out to be a speed. There's other things you can do. It turns out that the phase speed is also written as lambda f, or you can write it as lambda over capital T. Lots of things you can say. But anyways, so phase speed. So what's interesting is this thing inside of the argument of the sine function is actually an angle, and this angle is often referred to as phi, and in this case you can see that this angle is a function of position z and time t. So this thing, this function, is referred to as the phase, or the phase angle, and associated with this phase angle is a phase speed, and the phase speed is built out of these coefficients that sit in front of the space and the time parts of the angle. Okay, so there are other restrictions. So here's a really interesting restriction. E naught is perpendicular to B naught. This is a restriction, a requirement that is dictated by Maxwell's equations. That is, Maxwell's equations will never allow us to have an electromagnetic wave built out of electric field and magnetic field that are not perpendicular. Or that's the idea. So E naught is perpendicular to B naught, but even more, so let me put also the velocity. This is the velocity of our wave, right? The traveling wave. You know that it's got the speed of light, so the magnitude of this is the speed of light, but the velocity is actually proportional to the cross product of E and B. So E cross B has the direction of the traveling wave. So it's proportional to the velocity. In fact, actually, there's a really cool vector. Or actually, let me see. Let me make sure I'm saying everything I want to say. Yeah, okay. So there is a vector that tells us how energy is transferred by this electromagnetic wave, and this vector is called the Poynting vector, and it's given a special symbol. It's given the symbol capital S, and it is constructed this way. All you do is take the electric field component of our wave, take the vector cross product with the magnetic component, but then you go and you divide by mu sub 0. And this vector that you can make is actually, it's got dimensions of energy per time per area. Energy per time per area, or power. Power is energy per time, and then it's a power distributed over an area. Okay, yeah, so this is an important vector to realize. Cool, so that's called the Poynting vector. All right, so what I would like to do now is draw pictures of this wave, right? And this is when we can start to have an idea about a model, right? It's actually a picture model, or like, how do we think about this wave as a picture? But actually the model is more than that. The model for us, because it's a physics model, is also about energy, right? Energy is a big deal in physics, and we are also thinking still about this model in terms of energy, in terms of distances or positions, and also in terms of time. There's a dynamical component, right? So all of this is fitting into our thinking about this model. But now, let's have a picture, right? Picture of this model. So there's a couple of pictures. So let me copy this over. I forgot. I'm so sorry. This lecture's feeling really sloppy. But there is another restriction, and I really need to point this out. Maxwell's equations also give us a restriction that if you take this vector out in front, it's actually related to the vector out in front in here. That is, not only do these parts of the electromagnetic wave have to have exactly the same shape at the same time at the same place, but these two waves also have a restriction between what's referred to as their amplitudes, their amplitude vectors. It turns out that the relationship is the speed of light. So this is very important as well. It's another restriction dictated by Maxwell's equations. So there's restrictions about directions, right? The relative directions between the travel direction, the direction of the electric field, the direction of the magnetic field. Necessarily a very three-dimensional issue. They are all mutually perpendicular things. But not only that, there is, I'm so sorry, let's be very careful here. It's not their vectors, it's really their magnitudes, right? So the magnitudes are related by a relative factor of the speed of light. Okay, so pictures of this wave model. So we have this wave varies over the z direction as a sine wave, and this wave also varies exactly the same way over the z direction, but it turns out that they have to be perpendicular, and also they have to be each perpendicular to the direction of motion, which is the z direction. So the velocity is the direction of travel. That's the direction of travel. So our wave is traveling up the z-axis, or along the z-axis. So let me draw this slightly differently. So here's the z-axis. I'm going to imagine pointing everything in sort of this direction. So I'm going to imagine the I direction up, the y direction this way, and the z direction that way. So here is the x direction. Here is the y direction. And here is the z direction. And I'm going to just pick arbitrarily that the electric field has a magnitude that's equal to something in the I hat direction, where E naught is a constant, number of newtons per coulomb in the I hat direction. So the electric field is going to oscillate in the x direction. So remember, this is z. So here is a sine wave along the z direction that is transverse to the z in the x. So, and then, because E cross B needs to be the direction of motion, the direction of motion is down the z-axis. So the way that this can work out is if the B points this way at the same time. So let me continue this. I hope you can sort of detect how I am drawing these two waves. But in particular, check this out. This is a big deal. Wherever, right? Wherever E equals to 0, B equals to 0 also at the same time. That's a restriction. It's a restriction that Maxwell's equations imposed. The way we see it is that the shapes are the same, right? At the same time, at the same place, right? That's the wherever part. At the same time, if this is 0, that's also 0, right? So absolutely true. But also, check this out. Over here, the electric field is in the I hat direction. The magnetic field is in the J hat direction. And I hat cross J hat equals K hat. This is the velocity's direction. So the velocity of the wave is traveling out the z-axis. This is the direction of the magnetic field at that place, at that time. And I hat is the direction of the electric field at that place, at that time. Okay, but you can also check here, that spot is minus I hat. And this spot, right, is in the negative j hat direction. And it turns out that minus I hat cross minus j hat is also still, it's minus 1 squared k hat, right? And minus 1 squared is still plus 1. So that electric field, this magnetic field, also indicates a vector direction of travel of k hat. So this is the idea. So notice, though, this is a big notice. Note. These directions, the y and the x, the truth is this is terrible notation. These aren't spatial, that they're spatial directions, but what I'm graphing is not coordinates x and y. I'm actually graphing the strength of the electric field in the x direction and the strength of the magnetic field in the y direction. That's what this graph is. This axis is magnetic field units axis, and this axis is electric field units axis. But this axis is genuinely the z-axis. It's the position axis in the z direction. That's a big note. So this is a drawing of a light wave on the following three axes. It's the electric field axis in the x direction, magnetic field axis in the y direction, and the plain old location in space called the z direction, right? So yeah, and this is why we can talk about what's referred to as a plane wave. So let me draw a picture. So I'm going to actually draw the x direction, the y direction, and the z direction. And I'm going to indicate some planes. So, for example, this place right here on the z-axis represents a plane so this plane is, can you see it's got x direction and y direction like this. So these are a bunch of x, y positions for a particular value of z. And here is another plane that is elsewhere on the z-axis. So let me pick this position as this place on the z-axis, and the idea is everywhere in this plane at that particular z position, at all the values of x and y, the value of the electric field is the same everywhere in this plane. But also everywhere in this plane, for all values of x and y location at that particular value of z, is magnetic field that all points the same direction as well. It points in the positive y direction. This is the sense in which we are talking about a plane wave, because what if this position is instead here, right? Then in that position, the magnetic field actually points everywhere in the negative y direction at all the y values and the x values. The magnetic field has the same value in the plane. It is a plane wave. And the electric field also has the same value everywhere for this particular value of z at this moment in time. And the sense in which this is a plane wave is because these planes of constant value of electric and magnetic field vectors is traveling along the z-axis at the speed c, right? So it travels up the axis. We might say that the velocity of the planes is equal to c times k hat, right? The k hat direction is the z. And this plane is also traveling along the positive z-axis, or in the positive z-axis direction, also with the velocity of c k hat. This is the sense in which we have a plane wave. And this is a picture, it's a model picture of our traveling wave. at the position here in that plane, all x and y values are 0 for the electric and magnetic field, right? For all the values of x and y at that middle position z. And then there are in-between cases, of course. Okay, so let me continue talking here. Okay, so the Poynting vector has dimensions of energy per time times area, right? Or also known as power per area. That's the Poynting vector, the thing I mentioned before called S, which is you just take E, which in general is a function of x, y, z, and t, and you take the vector cross product of the magnetic field, which is a function in general of x, y, z, and t, right? And this is the vector cross product, not an x. And then you divide by the permeability of free space, comes from magnetism, thinking about how magnetic field spreads in space around a current. So anyways, so this is this thing, it's a power per area, and this you can think of in terms of the word brightness. Brightness. How bright is our light? And if you go through, you can study a quantity called the intensity. The intensity is sort of like a time average of the power per area. And it turns out that this intensity can be written it's sort of got a lot to do with some of the restrictions that come with Maxwell's equations. But if you do a bit of time averaging and thinking, let's call the intensity I. It turns out that it's got this form. It's 1 over 2 times mu naught C. And then it's the magnitude of the electric field part of the electromagnetic wave squared. So the following is a huge model note. Brightness does not depend on wavelength or frequency. In this model of light, what makes light bright or dim is not wavelength or frequency, right? This brightness does not depend on these qualities. The brightness depends on the amplitude of the wave. What the brightness depends on is how big this is, and this are related in this restriction way. But yeah, so brightness for the wave model of light, this is a really, really big model note. Brightness is independent of wavelength and frequency. You'll see that the particle version, the photon version, is brightness has something to do with frequency. Frequency and energy are intimately related in the photon model. Okay, so that's a really big clue. Maybe I'll put a big star next to it because I think it's important. All right, so then let's see. I've only got 2 other things to try to show you in this ultra sloppy crash course in the wave model of light. So how do we understand multiple light waves, right? So the way we understand that is, since light waves are just fields, right? And it is true the fields vary in time and space. Fields combine with the superposition principle. Fields combine with the superposition principle. That is, if you have multiple light waves, sometimes, a light coming from this direction and light coming from that direction, they may overlap in space, and at that overlap, you just use the superposition principle to understand what the overlap looks like. This is the model for how light behaves. It depends on the superposition principle, this linear combination principle. I think that this is a huge deal, and the idea is this is central to what is meant by wavy behavior. The superposition principle, the way fields combine, and in particular our light wave model, the way two light waves combine in space and time, is simply the superposition principle. That's a big deal. Let me expand the size of this exclamation point. Okay, big deal. And I have only one more thing as a model note. Let's think about this. Here's an object. It's made out of charge. Right? It's made out of electric charge. It's an object. It's made out of atoms. Atoms have nucleuses, electrons, protons, neutrons. Right? It's some object. I don't know if it's really big or small. Doesn't matter if it's metal necessarily, but it's some object. And if I use some source of light, here is a flashlight, say. Right? I've got batteries. And these batteries are used up as this flashlight sprays out light. So I'm converting the energy that's stored up in the battery into this light. As the light, so I'm kind of drawing these like plane waves. As these plane waves travel, right, this is the delivery mechanism of energy from the source to the, I'm going to call it a detector. This is our object, also known as a detector. It's the thing that's going to be able to take in the energy and information that's being delivered by the light. Right, so let's imagine it gets there. Can absorb the energy. Right, so if this is a traveling electromagnetic wave, electric and magnetic fields can shake charge. So you can, right, you can excite the electric charges in here. Yeah, so this is the sense in which we can pass energy from one place to another via these Maxwell equation predicted energy delivering mechanism called light. Okay, yeah, this is the idea.